Imagine standing barefoot on a lonely beach, the cold surf lapping at your ankles, and knowing that a top predator prowls the shallows nearby, then watching it vanish as if swallowed by the sea itself. Not missing for hours or days, but gone without a trace. That's the real mystery that sent a team of marine scientists into a puzzle worthy of a detective novel. Today we're going to unpack the strange, true story of Shark Alpha, the tagged great white that disappeared, the baffling clues its tag left behind, and the chilling conclusion researchers finally reached. Off the broad, windswept coast of Western Australia, researchers were carrying out a routine study, track great white sharks to understand where they go, how deep they dive, and what the ocean looks like from a shark's point of view. The team fitted several animals with archival tags, little data recorders that log temperature, depth, and movement. One of those sharks was a healthy 9-foot female, calm and strong, the sort of adult great white scientists expect to see patrolling the coastline. For months she behaved like a textbook example of a coastal great white, cruising, hunting, diving, returning. Then, unexpectedly, her tag washed up on a nearby beach. That happens. Tags can fail, come loose, or be knocked off. What the team found when they downloaded the data, though, stopped everything. The tag's log showed a sudden, instantaneous spike in temperature, from roughly 46 degrees Fahrenheit to about 78 degrees Fahrenheit in the blink of an eye. Immediately afterward, the depth recorder went from shallow coastal readings to a violent plunge down nearly 1,900 feet. The tag remained warm and moved in a slow, controlled pattern before finally being released and drifting back to the surface days later. Those two facts, the instant heat spike and the forced deep descent, told a single, terrifying story: the tag hadn't fallen off. It had been swallowed. When scientists first read the data, the simplest explanation rose to the top: another, much larger great white shark had attacked and eaten the 9-foot female. It sounds dramatic, but shark-on-shark predation is not unheard of. Large sharks sometimes treat smaller sharks as just another food item, a moving package of fat and protein. The recorded temperature of about 78 degrees Fahrenheit fits with the notion that the tag sat inside a warm-bodied predator while digestion began. The deep, slow descent matched behavior observed when a large shark takes a big meal into deeper, quieter waters to digest. Putting the pieces together, researchers estimated the predator could have been at least 16 feet long, possibly nearer 20, and built like a marine freight train. The digestion profile, the depth profile, the slow post-meal movement, all of it lined up with the physiology and behavior of a very large great white. In that light, the ocean hadn't revealed a new monster, it simply revealed a much, much larger member of a known species. But science rarely stops at a tidy explanation. Other ideas had to be tested. Science demands that you interrogate every plausible explanation. Could an orca, a killer whale, have been responsible? Orcas are known hunters of sharks in several parts of the world. They use clever techniques, flipping sharks onto their backs to immobilize them and often targeting the liver, which is rich in energy. But the orca theory has problems with the tag data. Orcas are warm-blooded mammals, their internal temperatures would likely show even higher readings than the 78 degrees Fahrenheit recorded. Orcas typically don't swallow large sharks whole and then drag them into abyssal depths immediately afterward. Could some giant deep-sea creature, a squid, perhaps, have done it? Giant squid are cold-blooded. Their flesh cannot maintain the warm stomach temperature recorded on the tag. They also don't show the dive and digest pattern evident in the data. And of course, there's the simple problem of force. Dragging a 9-foot shark 1,900 feet down would require enormous power. Then there's the ugly possibility of human interference. There are documented cases in modern times of people mutilating or killing great whites, removing livers, cutting off jaws, and otherwise desecrating these animals. Stories from fishers and even documented legal cases have shown humans can and do injure or kill sharks. But the tag's signature of a sudden internal warmth followed by a controlled, deep descent is very difficult to reconcile with human capture or mutilation. Rope marks, cut jaws, or being hauled aboard a vessel don't produce the same warm stomach and deep dive fingerprints. In short, the data pointed away from humans as primary actors. After ticking off each alternative against the hard evidence, one conclusion remained the most plausible and painfully clear: a very large great white shark had likely eaten the 9-foot female. One of the most important outcomes of this event wasn't just the conclusion itself but the way scientists changed how they treat odd tag data. The team that recovered the tag brought together tagging specialists, oceanographers, and even investigators experienced in ecological crime scenes. They moved slowly, line by line, treating the tag's record as if it were a digital witness. That attitude shift mattered. For years, researchers concentrated on tracking movement, migration, and basic ecology. Rare or extremist events, unusual attacks, mysterious disappearances, were often treated as blips or dismissed as equipment malfunctions. Shark Alpha's case forced a reconsideration. Small anomalies in tag data could represent extraordinary events. Suddenly rare spikes, abrupt dives, and anomalous warm recordings were not to be shrugged off but to be treated as potential evidence pointing to interactions we had not suspected or observed. And once researchers started looking for those anomalies, they found more. Other tag logs recorded sudden temperature spikes and rapid drops that could be read as similar predation events. The events were scattered and rare, but they were there. What had once been invisible became detectable the moment scientists changed their lens. Even with the tag's clear story, no one ever saw the predator. High-resolution sonar surveys and deep-water camera drops across thousands of square miles turned up no smoking gun. Sonar pings flickered and vanished, promising blips that dissolved into silence. The ocean proved once more how good it is at hiding big things in plain water. This absence of direct sightings keeps the case haunting. Was this an enormous solitary great white, a rare outlier in body size? Or might there be more than one such behemoth moving through the deep, occasionally taking large sharks? The tag data alone cannot answer the question fully. What the case did do was broaden scientific focus. Tagging programs began to flag anomalies, research teams prioritized long-term datasets over quick snapshots, and citizen scientists, fishers, recreational boaters, and coastal residents, became part of a larger net for reporting unusual sightings or findings. The ocean didn't surrender a face to the mystery, but it forced science to adopt better tools and to be open to strange, once dismissed signals. To appreciate how remarkable a predator would have to be to swallow a 9-foot great white, it helps to understand the biology of great whites themselves. These sharks, Carcharodon carcharias, are superbly designed for predation. Big individuals can reach lengths near 20 feet and weigh thousands of pounds. Their bodies are torpedo-shaped for bursts of speed, propelled by a crescent-shaped tail. Their teeth are multiple-rowed, continually replaceable, and built to slice through flesh and bone. Bite force models suggest the largest great whites can exert astonishing power. Estimates in some studies go into the tens of thousands of newtons. Their skeletons are made of cartilage, not bone, which saves weight and aids agility. Their musculature mixes white muscle for explosive ambushes with central red muscles suited for sustained travel, letting these animals both sprint and migrate long distances. Crucially, great whites have a kind of partial endothermy. They retain heat in core muscles and around the stomach. That physiological trait helps explain the tag's warm reading while inside a predator's gut. It also underlines why a big white could afford to digest large, high-energy meals in deeper, cooler water. Far from being indiscriminate killers, great whites are selective. Studies show they often hunt by sight and prefer high-fat prey. Seals and sea lions top the menu. They will test unfamiliar prey with a bite and typically release and reassess before committing, a hunting method that explains many non-fatal human shark encounters. Social dynamics among feeding sharks are subtle too. Dominance is shown through displays rather than endless fighting, with certain behaviors like tail slap signaling priority at a carcass. Bringing this back to Shark Alpha, it's plausible that a larger shark saw the smaller female as a substantial, energy-rich meal and acted with the efficiency of a predator that had evolved to take advantage of rare but massive caloric opportunities. Shark Alpha's story isn't just biology and detective work, it's part of a larger human narrative. Sharks have been in our stories for millennia, from Greek vase paintings and Roman mosaics to sea captain logs and modern films. For centuries they were frequent, sometimes deadly, neighbors to people who depended on the sea. Over the last century, however, humans dramatically reduced many shark populations through fishing, habitat change, and targeted killing. What we think of as normal numbers of sharks today are often a pale shadow of historical abundance. That historical context matters because it shapes how we interpret the ocean now. A shrimp-sized dataset may make a rare event look extraordinary. Conversely, an ancient abundance of predators could mean behaviors we rarely see today were once more common. Shark Alpha's disappearance forced scientists, historians, and the public to remember that our baseline for ordinary may be skewed by decades of human impact. The case of Shark Alpha did more than solve a local mystery, it changed practice. Researchers now treat tag anomalies as potential windows into rare predator interactions. The event pushed for better, longer-term datasets, cross-discipline collaboration, and public engagement in marine science. And for the rest of us, there's a humbling takeaway: even apex predators can be prey. The ocean houses dynamics we only begin to understand, and the line between hunter and hunted can shift depending on size, circumstance, and opportunity. The deep sea still keeps many of its big secrets, and when it chooses to reveal one, it does so in data as stark and simple as a temperature spike and a descent into the dark. We still don't know everything. Was the predator a single, enormous great white or a small population of unusually large individuals? How common are these predation events, and could they reshape how we think about marine ecosystems? Will improved tagging and broader surveillance finally catch a direct sighting? If nothing else, Shark Alpha's story reminds us to listen closely to the quiet signals, the odd spike in a data file, the curious absence of a tagged animal, the tale that a small instrument washes up and tells when nobody else can. The ocean speaks in subtle patterns, we just have to learn a better way to hear them. What do you think happened to Shark Alpha? Did the ocean simply reveal an unusually large great white, or is there more lurking in the deep than we can imagine? Share your thoughts below, and if this story hooked you, there's more where this came from.